We're continuing on section 15.3, implicit partial derivatives. And suppose that you have a surface in R3 and that is implicitly defined by an equation of x and y and z. Can you implicitly differentiate to find the slopes of tangent line to that surface? And the answer is yes. So in this time, and the process goes like this, because it's not just simple taking derivative, right? And you're trying to find partial respect to, let's say, x and partial respect to y. And so in that case, if you're finding partial z with respect to x, differentiate both sides of the equation with respect to x, treating y as a constant and z as a function of x. If you remember this in calculus of one variable, you would treat y as function of x. And that was it. Now y is going to be constant and z is going to be a function of x. And then you solve for partial of z with respect to x. So in this case, you again holding y constant, and that gives you a curve on the surface that in the direction of x, and you're taking the derivative of z with respect to x on that curve. To find, of course, partial of z with respect to y, differentiate with respect to y, treating x as a constant and z as a function of x. Then solve for the partial of z with respect to y. So now let's try to take the partial implicit partial derivative of this function, this surface that was given. So let's find example 3. Find the partial derivative of z with respect to x, partial derivative of z with respect to y implicitly from the function x times y plus x times z plus surface x times y plus x times z plus y squared z minus e to the power yz equal to 1. If you're finding the partial with respect to x, you're setting y equal to a constant. And then z is going to be a function of x. So here, constant times x, and now I'm taking derivative partial with respect to x, so this is going to be just a constant. Then x times z, two functions, product of two functions, so you have to do them as a product rule. So derivative of x times z, which is 1 times z, plus x times derivative of z. What is derivative of z? That's the partial of z with respect to x. And then now these two were one term, derivative of one term. Now you have y squared times z. Y squared is constant and stays. Derivative of z is just partial of z with respect to x. Then you have negative e to the power yz. E to the negative, the derivative of exponential is itself times the derivative of the exponent, which is y is constant and partial z partial x equal to 0. Now that you have that, you solve for z. You solve for partial z with respect to x. So basically, what do we have here? We have this term has partial z with respect to x, and this term has partial, and this term has partial with respect to x. So maybe move y and z to the other side and factor partial of x with respect to z on this side. And if you factor, you get x plus y squared minus e to the power yz times y partial of z with respect to x is equal to negative y minus z. Now solving will give me partial of z with respect to x is equal to negative y minus z over x plus y squared minus y e to the power yz. So this is partial with respect to x. Now let's do partial with respect to y. So to do partial with respect to y, you have to set x equal to constant. So here, if x is equal to constant, here, derivative of x times y is just going to be x. X times y with respect to y is just x. And derivative of x times z is x times partial of z with respect to y. Derivative of y squared times z is a product rule. Derivative of y squared is 2y times z plus derivative plus y squared times partial of z with respect to y. Now, e to the power of negative yz is going to be e to the power negative e to the power yz and times derivative of the exponent, which is a product rule again. Z plus y partial of z with respect to y equal to 0. Now again, you solve for partial of y with respect to z, remembering that you have to distribute here, and you get two terms. One has partial of z with respect to y, the other one doesn't. Put all the partials with respect to z on one side and solve. And the answer is going to be partial of z over with respect to y is equal to z e to the power yz minus x minus 2yz plus over x plus y squared minus y e to the power yz. So partial derivatives of functions of n variable are defined in the same way. For example, in a 3-variable function f of x, y, z, we calculate f of z by differentiating with respect to f sum z by differentiating with respect to z, treating x and y as constant. Now, find the partial derivative of f of x and y and z equal to z natural log of x squared plus y squared plus sine of xy. So let's start with partial with respect to x. Partial with respect to x, we have to set y and z both as constant. So we're trying to find partial with respect to x of f. See, this is 3 inputs and 1 output again, right? And z is going to be this time around z is going to be a constant because we're taking derivative with respect to x, and out of the inputs, only the one that we're taking the partial respect to should be a non-constant when you're taking derivative. So it would be z, derivative of natural log is 1 over x squared plus y squared and times derivative of inside with respect to x is just 2x, and plus sine of xc, derivative of that is cosine xc times derivative of inside, and x is the variable, z is the constant, so it would be z times. Now let's take the derivative with respect to y. This time x and z are constant, so z stays here again, 1 over x squared plus y squared times, this time x squared is constant, so it would be 2 times y, and again we get cosine, oh hold on, x and z are both constants, so we get 0 in here. Sine of a constant is 0. Now how about derivative of partial of f with respect to z? This time x and y are the constant, so natural log of x squared plus y squared is just a constant. It's like ln of 3 plus 4, natural log of 3 plus 4, and so it's just constant. So derivative is just derivative of z times that, natural log of x squared plus y squared, and then sine of xc, because sine of it's not a constant inside, it would be cosine xc times the derivative of the inside with respect to z, you get an x in there. So at each step we were very careful to set all the when we were taking partial with respect to each variable, input variable, we set the other input variables to a constant, and we continue. So this is different from implicit differentiation, because implicit differentiation they are all the variables of are connected to each other by an equation. Here there is the output variable, so you have input variables and output variables. So z is still input variable there, and z can be considered as implicit function of x and y in the previous page that we did.